The cold hit Volkov like a wall the moment he stepped outside, not the polite cold of city winters, not the manageable bite of a bad November morning. This was Alaskan cold, the kind that punishes hesitation, that finds a gap between your collar and your hat, and drives straight through to the bone. Volkov had lived with it for 31 years. He had stopped fighting it somewhere around year 3. Now, he just moved through it, the way water moves through rock, patient, purposeful, and utterly without complaint. He planted the shovel into the snowpack in front of the Quonset doors and leaned into it, throwing the weight of his shoulders behind the blade. The snow came away in heavy, compressed slabs behind him, through the gap in the corrugated steel doors. The wood stove threw its amber light across the white ground, and the warmth rolled out in visible waves, meeting the frozen air and dissolving into steam. Volkov did not look back at it. He knew it was there. It had always been there. The hut had been burning through winter since before he arrived, and if he had anything to say about it, it would be burning through winters long after he was gone. People asked him sometimes, visitors, journalists, the occasional government surveyor who came through with clipboards in polite disbelief, how the structure was still standing. They said it with a particular tone, the tone of people who had read something somewhere and now considered themselves informed. They said that Quonset huts were temporary, military surplus. Wartime construction meant to last a deployment, not a lifetime. They said the builders themselves had given these structures 5 years, maybe 10 if the conditions were kind. They gestured at the arched roof, at the rust-streaked seams, at the age visible in every bolt and rivet, and they waited for Volkov to agree that the whole thing was a miracle, an anomaly, a lucky accident of survival. Volkov never agreed. He just looked at them the way he looked at the cold, steadily, without drama, and said the same thing every time. It is standing because someone understood what they were building. And here's the part the construction industry does not want you to sit with too long. The people who built it were not architects with degrees on their walls. They were not contractors with liability insurance and project management software. They were enlisted men and government engineers working under the specific pressure of a world at war, with limited materials, limited time, and zero margin for philosophical error. And what they produce has outlasted nearly everything built in the decades since, by professionals, with far greater resources, in far more comfortable conditions. That is not an accident. That is a lesson. And the reason most people have never heard it explained clearly is that the lesson is inconvenient for an industry that profits from replacement. The Quonset hut was born in 1941 at Quonset Point Naval Air Station in Rhode Island, and it was born fast. The United States had just entered the war and needed structures immediately, not in 18 months, not after permits cleared, not after the environmental impact assessments and the contractor bids and the value engineering rounds stripped out everything that actually mattered. Immediately, structures that could be packed into crates, shipped across oceans, and assembled by men who had never held a construction tool in their lives. Structures that had to work in jungles and deserts and Arctic conditions, often simultaneously, because the war did not organize itself geographically for anyone's convenience. The design they landed on borrowed from a British precedent. The Nissen hut, developed in the First World War, but was refined for American manufacturing scale and American material realities. A half-cylinder of corrugated galvanized steel. No corners, no flat roof, no complex joinery, just an arch, repeated in panels, bolted together along overlapping seams, sitting on a simple foundation that could be adapted to whatever ground was available. They built over 170,000 of them during the war. That number matters, because what happened after the war matters even more. When the military declared these structures surplus, they spread across the country and eventually across the world. Farmers bought them, miners bought them, people in Alaska and Canada and the Northern Territories bought them and put them up on remote properties and expected them to last a few years before the weather won. The weather has not won. In most cases, the weather is not even close to winning. And the question you should be asking, the question that the people selling you modern prefab structures and engineered lumber and composite roofing systems would prefer you did not ask, is why? Start with the arch, because the arch is where everything begins. Modern residential construction is built almost entirely on right angles, vertical walls, Horizontal ceilings. Flat or gabled roofs with pitched surfaces that shed water at specific angles. This geometry is familiar. It is easy to frame. It maps neatly onto the rectangular lots that make up most developed land. And it has one significant structural weakness that every engineer knows, and almost no contractor will tell you directly. It concentrates load at specific points. When snow accumulates on a gabled roof, the weight presses down on the ridge beam, travels through the rafters, and arrives at the top plates of the walls. Those are the stress points. Those are the places where, in a heavy enough storm, in a building with any pre-existing weakness in the framing, things begin to fail. The roof sags at the ridge. The rafters crack at the bird's mouth cut. The walls push outward at the top plates. Every failure mode in a conventionally framed roof is a story about load that had nowhere to go except through a joint, and the joint that gave out. The arch has no joints in that sense. It has no ridge beam bearing a concentrated load. It has no rafters transferring stress to discrete connection points. The load applied to an arch travels continuously along the curve of the structure, following the geometry of the shape, and arrives at the footings distributed across a wide base rather than concentrated at specific nodes. This is why the Romans built arches. This is why cathedrals are built with arched vaulting. This is why bridge engineers default to the arch when they need to carry the heaviest loads across the longest spans. The arch is not a style choice. It is the most efficient load path that geometry provides. When Volkov watched snow pile on a Quonset roof, and he had watched it pile deep, deeper than most residential structures are rated to handle, he was watching the arch do what it had always done. The load pressed down. The curve accepted it. The stress traveled outward and down, arriving at the base of the walls where it was absorbed by the ground. The structure did not groan dramatically. It did not deflect in ways you could see. It simply held, the way things hold when they are shaped correctly for forces they face. He had seen a neighbor's machine shed, conventional post-frame construction, steel cladding on a rectangular frame, lose its roof in a loading event that the Quonset handled without visible effect. Same storm. Same snow density, different geometry, different outcome. Now consider the corrugations, because most people look at the rippled surface of a Quonset panel and see texture. What they are actually looking at is engineering. Thin gauge steel is flexible. That is not a criticism. It is a physical reality. An 18 gauge steel panel, held flat, will bend under relatively modest loads. It will buckle under compression. It will deflect under point loads in ways that compromise its structural function. If you try to build a Quonset from flat steel panels of the same gauge, the structure will be significantly weaker than what you actually get, and it would fail in ways that the corrugated version simply does not. The corrugation changes the geometry of the panel, and changing the geometry changes the structural behavior in ways that go far beyond what the weight of the material would suggest. Each ridge and valley in the corrugated surface acts as a miniature beam running the length of the panel. The material that would otherwise be a flat surface subject to bending in every direction becomes a series of interlocking structural elements, each one reinforcing its neighbors. The resistance to bending across the corrugations increases dramatically. The resistance to buckling under axial load increases dramatically. The panel becomes, in engineering terms, a much stiffer and stronger element than its material weight would imply. This is the same principle that makes cardboard boxes hold weight that would seem impossible for their mass. The fluting between the face sheets of a cardboard box is corrugation at small scale, doing exactly what the Quonset corrugation does at large scale, converting a flat surface into a structural form with genuine load-carrying capacity. You have held a corrugated cardboard box that weighed almost nothing and supported 40 pounds of books. That was not magic. That was geometry. Scale the geometry up to 18-gauge galvanized steel, curve into an arch, and you have a structure whose performance under load exceeds what any reasonable analysis of its material cost and weight would predict. This is why the engineers who assessed Volkov's hut came away with the results they did. The structure was not overbuilt. It was correctly built, which turns out to be rarer and more valuable than overbuilt. Because correct geometry is what actually carries load, not the mass of material you pile on top of a flawed design. Then there is a question of the foundation, which is a place where most permanent structures in cold climates eventually fail, and a place where the Quonset's apparent weakness turns out to be its most sophisticated feature. Conventional construction wisdom says foundation depth equals permanence. Go deep, pour concrete, anchor the structure into the earth at a depth below the frost line, so that freeze-thaw cycles cannot move it. This logic is sound in many climates. In permafrost country, it is a path to structural failure that plays out over years rather than decades, slow enough that by the time it becomes obvious, the damage is already irreversible. Permafrost is not simply frozen ground. It is ground whose load-bearing capacity is entirely dependent on its remaining frozen. The ice crystals within permafrost soil are structural elements. Remove the ice by thawing, and you remove the structure. What remains is saturated, compressible soil with a fraction of its frozen load-bearing capacity. A heated building anchored with a deep concrete foundation in permafrost conducts heat into the soil through the foundation itself. The permafrost within the thermal influence of the foundation thaws. The thawed soil compresses unevenly. It rarely compresses uniformly, because soil composition and drainage vary, and the rigid concrete foundation, which cannot accommodate differential movement, transmits every millimeter of that differential settlement directly into the structure above. Walls crack, floor systems rack out of plane, door and window openings distort. In severe cases, entire corners of buildings drop, while others remain fixed, shearing the structure along diagonal lines that no amount of conventional repair can address without first solving the underlying thermal problem. Volkov's Quonset sat on treated timber sills resting on compacted gravel pads. The gravel was the key. Gravel has very low thermal conductivity. It does not efficiently transfer heat downward into the soil beneath it. The thermal influence of the building's interior warmth, traveling downward to the floor system, was interrupted by the gravel layer before it could reach the permafrost below. The permafrost stayed frozen. Its load-bearing capacity stayed intact. The timber sills, resting on the gravel, could be adjusted when seasonal movement shifted the structure, and in Alaska, seasonal movement is not a possibility but a certainty. The response was not a structural repair. It was a shimming operation. You identified where the sills had moved. You placed additional material to bring the structure back into level, and you were done. An afternoon's work, as Volkov had confirmed across 30 years and 3 shimming operations on the northwest corner. The original builder had not chosen this approach because he was too poor for concrete. He had chosen it because he understood the ground he was building on. That understanding was worth more than any quantity of poured concrete would have been. The galvanization question comes up whenever someone looks at a weathered Quonset and concludes it is deteriorating. The surface rust, the mottled gray and orange of aged steel, the visual evidence of decades of exposure that most people interpret as evidence of a structure in decline. They are misreading the evidence. The surface oxidation visible on a galvanized steel panel after 50 years of Alaskan exposure is not the steel corroding. It is the zinc corroding, which is precisely what the zinc is there to do. Galvanization is a process of applying a zinc coating to steel, and the zinc is not decorative. It is sacrificial. Zinc oxidizes preferentially to iron. Given the choice between zinc and iron as targets for electrochemical attack, oxidation will go after the zinc first. As long as zinc remains on the surface, the steel beneath it is protected. The zinc layer does not simply cover the steel and passively block moisture. It actively draws the electrochemical attack toward itself, away from the steel it covers. And as the zinc oxidizes, the zinc oxide it forms on the surface is itself relatively insoluble and adherent. It forms a patina that slows further oxidation of the remaining zinc beneath it. In a cold, dry climate, which is what interior Alaska provides so much of the year, this process is dramatically slower than it would be in a warm, humid environment. The electrochemical reactions that drive corrosion require moisture and proceed faster at higher temperatures. An Alaskan winter is approximately the worst possible environment for corrosion and the best possible environment for a galvanized steel structure that you want to last. When a materials specialist drilled test holes in Volkov's panels and found full-thickness steel beneath the surface patina, he was confirming what the chemistry had always suggested. The zinc had been doing its job for 50 years, consuming itself in thin layers on the surface, while the steel beneath it remained unaffected. The structure was not corroding. It was weathering, which is a different thing entirely. Weathering is managed deterioration. It has a rate, and the rate is slow enough that the structure's functional life extends far beyond any original projection. This is the information the construction industry does not emphasize, because the construction industry is organized around replacement cycles. A building material that weathers gracefully across 50 or 100 years without requiring replacement is a poor customer. A building material that requires replacement in 20 years is an excellent customer. The economics of this reality shape what gets promoted, what gets specified, and what gets built, not the engineering reality of what actually performs best over time. But Volkov would tell you, if you asked him directly and he was in a mood for honesty rather than silence, that the engineering alone does not explain the hut survival. The engineering was the precondition. The survival required something else. It required consistent attention from the people inside it. He inspected the bolt lines twice a year without exception, in late spring after the worst of the freeze-thaw stress had passed, and in early fall before the serious cold set in. He looked for fasteners that had worked loose under thermal cycling and tightened them. He looked for seams that had opened and sealed them with compound rated for the temperature range he was actually dealing with. Not whatever was at hand. Not the wrong compound applied by someone who assumed all sealants were equivalent, but material that flexed with the steel rather than cracking at -40 and allowing moisture infiltration at exactly the moment when moisture infiltration did the most damage. He kept the ventilation clear because he understood what happens to a metal structure that cannot breathe. Every meal cooked inside the hut, every breath drawn by the person living in it, every log burned in the wood stove generated moisture that had to go somewhere. In a properly ventilated structure, it went out through the ridge vent and the sidewall vents. In an improperly ventilated structure, it went into the air until the air became saturated, then it condensed on the coldest surfaces, which are the metal structure of the metal walls, and it sat there, liquid water against steel, initiating exactly the corrosion process that the galvanization was designed to prevent. You can have the best galvanized steel panels ever produced, installed by the most skilled builders who ever lived, and destroy them from the inside in 15 years by blocking the ventilation. The original builder had put in a ridge vent and 2 sidewall vents. Volkov had kept them clear for 30 years. 20 minutes of work per season. The difference between a hut that lasts and a hut that destroys itself invisibly from within. He cleared snow from the base of the walls after every significant storm, not because he had read that he should, but because he had thought through what ice buildup at the base actually did. Ice that formed against the lower edge of the panels during Thori freeze cycles. And in Alaska, Thori freeze cycles were constant at the shoulder seasons, expanded as it froze. That expansion was directed against whatever was in contact with the ice, against the lower edge of the corrugated panels. It was directed outward, levering the base of the panels away from the timber sills in increments too small to see in any single cycle, but cumulative across seasons. Open the base of the panels, and you open the structure to wind infiltration, moisture infiltration, and the beginning of a degradation cycle that accelerated with each subsequent winter. None of this was complicated. All of it required understanding what you were dealing with, and all of it required showing up. This is a part that does not fit neatly into any marketing narrative about durable structures, because it cannot be sold. You cannot purchase it as an upgrade. You cannot specify it in a building contract. The attention that Volkov gave to Quonset over 30 years, the inspections, the tightening, the sealing, the ventilation maintenance, the snow clearing, that attention was not a product. It was a practice. And the practice was what converted good engineering into actual longevity. The construction industry understands this on some level, which is why maintenance schedules exist. But the maintenance schedules assume a relationship between owner and structure that modern building culture has largely abandoned. People move. Properties change hands. The knowledge of what a specific structure needs, built up over years of direct observation, dissipates with every transfer of ownership. The new owner does not know that the northwest corner needs monitoring. The new owner does not know which sealant compound was used on the seams or why that specific compound was chosen. The new owner applies the wrong product, confidently, because it says it is from metal on the label, and 3 winters later the seams have failed, and moisture is doing what moisture does when given access to places it should not be. Volkov had been here 30 years. He knew this hut the way you know a thing you have lived alongside, not from its documentation, but from its behavior, its specific responses to specific conditions, the particular way it moved in certain temperatures, and the particular sounds it made under certain loads. This knowledge had no market value. It was not transferable in any efficient way. But it was the reason the structure was still standing alongside the arch and the corrugations and the gravel pads and the galvanization and the ventilation system. All of those things together. Not any one of them alone. The surveyors who came 2 years ago had access to instruments Volkov did not. They had load testing equipment and moisture meters and ultrasonic thickness gauges, and the accumulated professional knowledge of careers spent assessing structures. They went to the hut for 3 hours with the systematic attention of people who had seen many things fail in many ways and knew what failure looked like in its early stages. At the end of 3 hours, the older surveyor had told Volkov that the structure rated better than most of what they currently permitted. Volkov had not been surprised. He had been confirmed. The man had looked up at the arch and said, almost himself, that they really knew what they were doing. And this was true. But it was also incomplete in the way that most things people say about engineering are incomplete when they leave out the human dimension. The engineers at Quonset Point had understood the arch and the corrugation and the thermal properties of galvanized steel in cold climates. The men who assembled the panels in the early 1970s on this Alaskan property had followed a design that encoded their predecessors' understanding in its geometry. And the men who had lived here since, including Volkov, standing now with his shovel in his hand in the dark of an Alaskan morning, had provided the one thing that the engineering could not provide for itself: presence, attention, the ordinary, unremarkable, absolutely essential work of knowing what you have and caring for it accordingly. The construction industry will tell you that modern materials are better. In some ways, this is true. The coatings are more sophisticated. The fasteners are more precisely engineered. The computational tools for structural analysis have capabilities that the Quonset Point engineers could not have imagined. None of this has produced structures that routinely outlast what those engineers built with corrugated steel and geometry, and the pressure and necessity bearing down on every decision they made. Necessity clarifies. It removes the option of complexity for its own sake. It drives you toward the essential, toward the thing that actually works under the conditions you actually face, without the luxury of adding expensive solutions to problems that a better fundamental design would have prevented in the first place. The Quonset was the product of necessity applied to engineering intelligence. What it became, over 50 years, was a product of that foundation maintained by human attention. Neither element was sufficient alone. Together, they produced something that confounded every expert who looked at it with expectations shaped by a construction culture that had stopped believing in the arch. Volkov finished clearing the doorway and stood for a moment in the opening. Looking back at the interior, the wood stove glowed in the far corner. The tools hung in their order on the iron hooks. The wood pile stood in its precise stacks against the curved wall. The arch overhead caught the firelight and distributed it evenly through the space, the curve doing what curves do, gathering, redirecting, making the most of what was given to it. He had stopped trying to explain the hut to people who were not prepared to hear it, not because the explanation was difficult, but because the explanation required the listener to accept something that modern building culture resisted, that the engineers who worked fastest under the most pressure with the fewest resources in the middle of a catastrophic war had understood something fundamental about structure and honesty and the relationship between a building and the forces it would face. And that understanding had produced something more durable than anything the subsequent decades of prosperity and technological advancement had managed to replace it with. The arch did not care about modern building codes. The corrugations did not care about current material specifications. The gravel pads did not care about what the permit application said about foundation requirements. The galvanization did not care about replacement cycles or warranty periods or the construction industry's financial interest in buildings that needed to be torn down and rebuilt within a generation. The physics did not care about any of it. The physics just worked the way physics always works, quietly, consistently, without drama, producing the same results every time the same conditions were met. Volkov had met the conditions. He had done it for 30 years. He picked up the shovel again. There was more snow at the door. There was always more snow at the door. He went back to work, The amber light at his back, the cold ahead of him, and the arch holding above it all exactly as it had always held, steadily, without complaint, and for longer than anyone who had not paid attention would have thought possible.